Okay, so today's objective is 6.2b. We're just applying, do some application of the base E equation of continuous growth or continuous decay. So we will be successful if we can use the PERT formula to solve real-world type word problems, or in other words, application. All right, so first, let's just review, and I'm going to color code each different piece of the PERT formula so that we can identify things in the word problems and kind of make some connections here. So here are the colors that I'm using, and you can choose whichever colors you like, of course. But I'm going to go ahead and I'm going to start with T. And I'm going to do T in purple. Now, T is representing time, and the reason that I'm starting with T is that it's our independent variable. It's representing the x-axis. So the time is variable. It can change. Everything else pretty much stays the same. So just remember when we're talking about time that you're paying attention to the units that time is being measured in, whether it's years or days or minutes or whatever. Okay? Then I'm going to switch to green. And we're going to talk about our starting point. So green means go. So I'm going to label my principal in green. Now today we won't be doing continuous interest problems like we were doing yesterday. We'll be using some continuous growth of populations, some continuous decay of a radioactive isotope, etc. So P doesn't always stand for principal. It could represent your starting amount. So we want to look for that as well. Then we'll go to R, which you know is your rate. We've discussed this, and I'm using red for a rate. Okay, make sure you put it in decimal form. And then, excuse me, E, what you're looking for so that you know that you're using this particular formula is you're looking for the word continuous. Whether it's continuous growth or it's continuous decay, you're looking for the word continuous. It could grow, it can decay, it can expand, it can decompose. So it might be different versions of growth and decay, but definitely continuous. And then with my pencil, I'll just talk about your A of T, which is your amount, your final amount after whatever time you've plugged in. So that's your amount after time. Okay, so as I mentioned to you before we began, today you have an opportunity to earn some extra credit when you do your assignment. And when I mean earn extra credit, I mean double your homework score. So instead of getting 10 out of 10, you could get up to 20 out of 10. I don't offer these opportunities often, so you know you're going to have to work for it. So let's take a look at this problem, and I'm going to illustrate how you get the regular points and then how you can double your points. So we're going to read through the problem the first time, and here's my advice, and maybe write it off to the side. You need to, if you're a good mathematician and you're a smart problem solver, define what it is you're supposed to find. And then set your problem up so that when you solve it, it tells you exactly the answer you want. And you don't have to do any conversions at the end. The more you practice this, the more skilled you become. So let's read the problem and focus on what we're supposed to find. 1980, the population of the U.S. was approximately 227 million. And the population has been growing continuously at a rate of 0.7% per year. That's a very slow rate. Okay, less than 1% a year. Predict the population N of T in the year 2010 if this growth trend continues. And P.S. that tells you how old the textbook is that I pulled this problem out of. 2010 was 8 years ago. But anyways, that's okay. Still, same problem. Math hasn't changed. Okay, so what are we supposed to find? What are we looking for? The N of T, which represents what? the population in 2010. So yeah, we're looking for the N of T, but 2010 is how many years? So we'll have to look at that. So we are definitely looking for the N of T. That's what we want to know. So we're going to do math in regards to that. So we're looking at a population. So let's think about whether or not we need to use our 227 million, our initial population, and if we want to leave it as 227, or if we want to write it out as 227 million. So let's think about that. If the population is growing at less than 1% per year, do you think my population is going to be in the billions? Or do you think it's going to stay in the 100 millions? 100 millions. So a smart mathematician is going to think, okay, I can probably go ahead and leave my initial or my amount as in the hundreds, and then we can just tag million onto our answer when we're done. So let's go back and grab our purple pencil and identify, where do we find time? How much time has passed? By subtracting 2010 minus 1980. So our time would be 2010 minus 1980, or 30 years. So that's the passage of 30 years. So we've defined that. Our T is defined. Okay, let's grab up our green pen and get our initial population, right? So I'm color coding here. So our initial population is 227 million, but let's not plug in the million part when we do the math. Okay, then I'm going to grab up my blue pen so that I can indicate in here in the word problem how I know I'm using the PERT formula. What's the word? Growing continuously. Actually, it's words. It's growing continuously. So that's how I know I'm going to use base E, because base E helps me to find that. And then all I need is my rate, which is here, right? But we have to convert it to decimal form. So that's what? 0.007. 0.007. Because you got to bounce the decimal 2 times. Don't forget that. All right, so let's go ahead and set up our problem. So we have the N of, and we're plugging in how many years? 30. So here's our independent variable. We're plugging in 30. And we get, do I have to color code, or can I just write it out? I can write it out. 227 e to the 0.007 times, is it 007? It's 0.07? Yeah. 0.00712. Oh man, where'd my brain go? Times 30. Okay, so we're going to get the population at year 30 is, you have calculators. Okay, so how about we just keep it in millions? So we'll call it approximately 280 million, because we were given an approximate amount at the beginning. It's acceptable to give an approximate amount at the end. Now, I'm going to treat you like you're a calculus student today. I expect to see the answer in 4 different ways. So that right there gains you your first point for the assignment, and it's worth, each problem's worth 2. So to get the second point and to get a 10 out of 10, you need to write a verbal answer, a complete sentence. What's the answer to this question? In 2000, I keep doing that. I keep doing that all day long. I've been writing 21. In 2010, the U.S. population is predicted to be, or was predicted to be, because it's already passed, right? Approximately 280 million. Okay, So that'll get you your credit for your homework. To do the math and give me a complete sentence, label your answer. You want extra credit points. I would like to see this answer, not just algebraically and verbally, but analytically and graphically. So here's how you're going to get the extra credit. So here's how you're going to do it. Analytically just means I want to give me some data. So analyze this problem by giving me a table of values where t is representing your x and n of t is representing your y. And we already know that at year 0, 1980, there were 227 million people. God bless you. All right. Now, here's the thing. I want to see at least 5 pairs of data on your analytics or your analysis. So we have 2 pairs of data already. We have year 0 and we have year 30. I suggest you get some in-between values and maybe in a value as a future value. So how about we go by 10s just as an example? So we'll do year 10, year 20, year 30 we already know is 280. And let's get one more, year 40. So analytics, we're analyzing here. So plug this data in and give me a value. In 10 years from 1980, which would have been in 1990, the population was approximately 243 million. Thank you. All right, 10 years later in the year 2000, you guys were tiny if you were even born yet. Well, I think most of you were born after the millennium. There's not many of you in here that are 18. 261 million. And then how about in 2020? 300 million. Okay, so analytically, that'll get you a point. So that's an analysis of the data, taking it a couple steps further. Now, this will help you to get your final point. I would also like to see graphically what this data looks like. But I am going to challenge you. This is an example of exponential growth, which means that your graph should curve. It should not be a straight line, which might be difficult to do. So be thoughtful. To get the point, your graph has to have a title that tells you what this graph is telling you. Has to have an x-axis that is labeled, a y-axis that is labeled, a good scale on your x and y axis. So what's your x-axis? What are we? Oh, let's title our graph. What is this about? Since when? Since 1980. And we would definitely want to mention since 1980, says 1980 is year 0. We're not going to go all the way out on our x-axis to 1980 and start graphing things. So that's a good title. So that'll get you some good data points right there. So this is our x-axis, and we're going to measure our x-axis in time, and we're measuring it in years. And what is our y-axis measuring? Population in what? In millions, for sure. Unless you want to change all of this to millions and graph up in the y in the millions, which would be a major pain, I think. Don't you? Okay, so we're going in increments of 10 on our x-axis, so we'll go 10, 20, 30, 40, maybe go all the way out to 50. I don't know. We didn't go out that far, so that's okay. And then we need to decide what kind of scale do we want to use on our x-axis. We've got data from 227 million to 300 million. So what kind of scale do you want to use? Hundreds? Do you think it'll be easy to find out where 227 is versus 243 if we're jumping by hundreds? Thousands? What if we did this? This is in hundreds, yes? So I don't want to go in thousands. That was a really good suggestion, Isaac. Sarcasm. Accordion down your y-axis. So let's put a break in the graph so that we don't have to graph any of the thousands, any of the 100 millions. Let's get into the 200 millions. So what if our graph started at 200 million? Because we've got a little break in our graph right here indicating that we're accordioning the graph down. Is that a word? I don't know. So what increments do you want to do? 10? We're going from 200 to 300. 25? Do you think you can fit 25s in there? What if we did 20? Okay, you do what you want. I'm going to do 20. 220, 240, 260, 280, 300. I'm going to go by 20s. You can choose your scale. All right. And then we're just going to graph our data. And actually, I'd like it if your data went, you know, that you went a little higher than your data caps out as, but we're kind of limited in space here. I might get a different color so I can see some points. So at 0 years, we were at 227 million. I guess you could put like some halfway, some tick marks in there for 10, and you could do that. That might be helpful. All right. And then at 10 years, we're at 243. At 20 years, we're at 261. 30 years, we're at 280. 40 years, we're at 300. And that looks really linear. But exponential growth is not linear. It's just that this graph is so accordioned down. It skews the y-axis quite a bit. So you don't even have to connect the data, but it would be good if maybe just put a little curve at the end with an arrow to indicate that you know that this is supposed to show exponential growth. So it should have a little bit of a curve in it. And then label it like this. The N of t is equal to 227e to the 0.007 t. So it's variable. I can plug in whatever time I want, and it'll give me the population at that time if the rate is consistent. Okay? So that is how you would get the extra credit. You got to work for it. I don't actually think that's very difficult. You just have to use your brain a little bit and plan it out. Okay? So that's what I'm asking for. Now for these next two problems, all I'm going to do is give you the answers to each one. And you have 30 minutes left of class. You can work them out. And here's something else I want to mention. You don't need to draw the graph or do the data table for either of these two problems, because it won't earn you any extra credit to put them in your note page. I'm not grading your note page. Well, I won't until the end of the semester. But for your homework, if you want the extra credit, you have to do the extra work. Okay, so for this next question, which will be really helpful for the hardest problem on your homework, the answer for the price per 1 acre is $343.35 per acre. And then the answer for the third one, which is quite a bit easier, is 43.10 milligrams. And I put the 0 on there because it says to round to the nearest hundredth. So that's why I went to 2 decimal places. Okay, so there's that. And just remember that your homework was problems 22, 25, 28 part B and C, because this right here is part A. This is 28A right here, this problem, which kind of helps you set up your table of values and your graph. And then number 32. So I'm giving you 4 problems to work on. Okay? All right. So off you go.